We are hearing more and more about neuromorphic devices. And in fact, MRS Bulletin is planning a theme issue on this topic next year. What are the main approaches, and why is material science so critical to their success?
So, okay, so first I'm going to give you a little bit of background, because there's some very specific neuromorphic devices that are really hot in industry right now. And the deep background is that in the last couple of years, neural networks have had a remarkable amount of success. The application that really put them on the map recently was Google Translate, that could be done with a neural net sort of program. Now, when you think of a neural net, okay, there are various nodes that are coupled together with some coupling constant, okay? And determining that coupling constant is a key to getting these things to work well. All right, now let's go to the device picture. The device picture is right now, that's all done in software, okay? But think about how much better it would be if instead of doing it all in software, you actually had a hardware implementation. So instead of having a constant someplace in the program, you actually have a variable resistor that connected the two nodes together. So think of just like a potentiometer, that you're going to tweak it and tune the potentiometer till you get the right coupling constant, and the English sentence appears in French, okay, or whatever it is that you want to do.
Interesting.
Okay, so that's sort of the driving force for it. Now, it turns out that a lot of physics isn't terribly linear, and a lot of material science isn't terribly linear. So the tricky thing is to try to make these things so they behave linearly. Now, I'll go through a couple of the really strong contenders for making this kind of device. Right? That was the original question, I think. Okay, so sort of one of the leading contenders is based on a technology called RAM, which is resistive random access memory. So the idea here is taking, instead of a good solid insulator, taking a kind of leaky insulator, and then by applying voltage, push around oxygen vacancies to change it from being an insulator to a conductor and back and forth. Okay, this is a really heavily developed approach. A lot of people are betting on this one. Now, the drawbacks are it's highly nonlinear, it's stochastic, so you're never quite sure what you're going to get. All right. So those are sort of the scary aspects of it. So then there's another technology which is based on phase change memory. And phase change memory has been highly developed for just for digital 0-1 sort of thing. But the idea here is, well, maybe you could put in an intermediate state in between a 0 and a 1. So by changing whether something is crystalline or amorphous, you change its resistivity. So that's heavily developed. But a common problem with both of these things is we're taking something that was developed for digital technology, 0 or 1, and we're trying to force it into an analog technology. And to really get there, I mean, we just spent decades making sure these things were 0 or 1.
Yes.
And now we're turning around and putting them into an intermediate step. Third technology is the one that I've actually been working on, which is called Electrochemical Ram. And the idea here is to take an insulator and intercalate an ion into it to change it into a conductor. Now that sounds really exotic, but it turns out that your rear view mirror in your car works this way.
Oh.
Okay, it changes its reflectivity by changing from an insulator to a conductor, so it reflects light or absorbs light. So we're doing this using tungsten oxide and placing two contacts in the tungsten oxide. The tungsten oxide is sort of like a channel, just like in an FET. Then we have a medium that contains our intercalant. In this case, it's lithium. So you use an electrolyte, just like a solid-state battery, and you apply a voltage and drive lithium in and out of the channel to change its conductivity. Immense challenges in figuring out what are the mechanisms, what are the retention, and so on and so forth. So there's a lot of materials work to be done in all three of these approaches.
Fascinating, fascinating.